Last day we discussed about nonlinear functions, and to be more specifically, we have seen functions and graphs of second order or quadratic functions, right, whose graphs appear to be parabolas. Now we begin with an interesting practical application of these quadratic graphs. For example, consider a company with its profit function given as pi of x equal to 200x minus x squared minus 4000. Right. This is a quadratic function since the highest power of x, the unknown, is 2. Right. So we can rewrite this as, the question is to find the maximum profit. And suppose x is the number of units sold. See, the company is, the name of the company is A. So the company produces something, and this is the profit when the company sells x units of the same of the product, right? So we need to find the maximum profit, and when is that occurs, or the x value when the maximum profit occurs. Okay. So there are two things to be identified: the maximum possible profit and the x value, or the number of products to be sold to achieve the maximum profit. Okay. So look at the quadratic function given, and let's try to rewrite this as pi of x equal to minus of x minus 100 whole squared plus 6000. Are they the same? Are they the same? See, what is x minus 100 whole square? X square minus 200x minus 10,000. Sorry, plus 10,000. And this negative will be impacting on all of the terms inside. So this will be minus x square plus 200x minus 10,000, and plus this 6,000 will be reducing with the minus 10,000, and will be minus 4,000 will be rest over there. So this is actually the same. Why did we do this? We are actually transforming the given form of quadratic function to the well-known general form, which was something like a into x minus h whole square plus k or something, right? So that we can identify some information from this. See, how does the graph of such a function looks like? There are certain possibilities that the function may look like a parabola of this form, or the function may look like a parabola of this form, or in this type, or of this kind, right? In fact, we have seen that these two can be rolled out, since we have a function of x. See, we have seen only these two, which opens up and opens down. The other two will be discussed soon, later in the course. So we have these two choices, and see, as a function we have two axes. One is dedicated for x values and the other is for y values. And the y value here is pi of x, which is nothing but the profit. So profit is marked along the y axis. Similarly for this type too. So to find the maximum profit, we are supposed to find the maximum value on y axis to which the function extends up to. Right. So if this is the case and the function elongates to infinity here on both sides, we don't know what's the maximum profit, since we don't have anything finite or any specific portion where this gets terminated. This does not end anywhere, this goes forever. So we don't know what's happening there. But in this case, we have a minimum profit. We have a minimum profit which is at this point, which is the vertex. Right, vertex. This is the minimum profit since the function does not lie below that. It does not go down this point. Right. So what if our situation is of this kind? See, Here the function elongates downward to infinity, or it does not get terminated anywhere. But at the same time, we have a maximum value being attained by this function, which is again at the vertex. You can observe that the function does not lie anywhere above this point. So for a parabola which is opening upward, we may be unable to find a maximum value, but we can find a minimum value. Similarly, for a parabola opening downward, we may have some difficulties to find the minimum possible value, but we can identify the maximum value. Right. Now what about our parabola? So comparing with the general form, we got, it was not negative, a into x minus h whole square plus k. So comparing with the general form, we get a is equal to minus 1, h is equal to 100, k is equal to 6000. Right. We have learned to draw graphs of quadratic equations using this form. Right. The parabola opens up if a is positive. Parabola opens down if a is negative. Right. So a is negative 1 here. So our parabola opens downward. Somewhere, I don't know where is it. Right. Somewhere downward. And the vertex is given as hk. Right. So h is 100 here. K is 6000. Though this point is 100, 6000. We have seen that for a downward opening parabola, the maximum value is attained at the vertex, and the vertex is hk, which is 100, 6000. Right. And this is the x value and this is the y value at the vertex. We have seen that the profit is marked along the y-axis. So the maximum profit is 6,000 rupees maybe, and the x value or the number of units to be sold to attain the maximum profit is 100 units, right, which is the corresponding x value for 6,000. Right. So this is in fact very much similar, but your textbook made it a little complicated. So this is how we use quadratic functions and its graphing techniques to identify the maximum profit, or sometimes this may be on the other side, or we may use cost function. And similarly to the concept that profit is to be maximized, the cost has to be minimized for a profitable organization. So in that case, we may be having an inverted parabola or which opening upwards. Right. There are a lot of questions available in the textbook, which will be shared with you soon. So you can try to solve them up. Right. Now we move a little backwards. When we discussed about functions, when we introduced functions, I just forgot to tell you something. How does a function and an equation differ? What are the possible differences of an equation and function? Right. So I'll give you two cases. Well, suppose we have a function y equal to 2x, and we have another one, say y square equal to x. Right. So these two are equations at a view. Are they both functions, or are they not both functions, or any one of them are function, right? So I would like to introduce you a concept that for an equation to be a function, remember, for an equation to be a function, there should be a unique y value for any given x. Which means for any given x, you should be able to find a unique value for y, a single value for y. In other words, if you can find two values for y when you give a single value for x, such an equation is not considered as a function. Right, I'll repeat. If you can find two different values for y when you give a single value to x, such an equation will no longer be considered as an equation. sorry, a function, right? So what happens here in our cases? See, y equal to 2x. Whatever the value you give to x, y is obtained as the double of x, which means as you change x, y will be changed, and there will be only single value for y. See, any number have two doubles? No way. So this is a function. What about this? This is something interesting. So if I have y square equal to x, can I rewrite this as y equal to plus or minus root x? Right. This itself gives information that this is not a function, since if I consider x equal to 3, y square equal to x means y equal to plus or minus root x, and for x equal to 3, y of 3 or y equal to plus or minus root 3, which is in fact two values or minus root 3, which are no way equal, right? So sometimes this may happen that for a single x value you may have two y values, and in such a case such equations are not considered to be functions. So you can expect some questions like this. You might have given certain equations and determine which of them are functions, right? So this is how we algebraically determine whether an equation is a function or not. In the same way, we have a graphical technique to identify whether a given equation or a given graph is of a function or not. I'll start with an example. These are the axes. So I have given 4 graphs. We don't know what are the equations giving these graphs, but still we can determine whether the equations giving this graph are functions or not. That is called vertical line test. The test says that if you can draw a vertical line touching at least at 2 points of the graph, such a graph will not be of the function. So if you can draw a vertical line touching at least at 2 points of a graph, such a graph will not be of a function, right? So what about this case? Wherever we draw a line, such a line will not intersect the graph at more than one time or at more than one point. What about this? Wherever you draw a line, that line may intersect the graph at 2 points of the circle, at 2 points of the graph, right? So this is not the graph of a function according to our test. What about this? See, this goes a little slanted, right? So if you draw lines, no line will intersect the graph at 2 points. So this is again of a function. What about this? If you draw lines, see, lines up to this point does not intersect the graph twice, but once you start to draw a line at this point, this coincides with the graph at more than one points. In fact, this coincides with the whole part of graph, right? So this is not a function. This graph is not of a function. So remember, we does not need all the lines to intersect twice. At least one line make a contact with the graph at least twice. Such a graph will not be considered as a function, right? So we can make use of this technique as well to identify whether the given graph or equation is of a function, right? So that's all about the introduction of functions, and now we move on to a little more complicated ideas in calculus. Let's start with limits. So when we defined a function, we have seen that a function is actually connecting two variables, a variable y and a variable x, with some equations. And as x varies, see, we call x to be the independent variable. As x varies somewhere, it changes y as well, right? Or for example, if we have a function y of x equal to say x square, as x varies or x changes its value, y also changes its value. For x equal to 0, the value of y is 0. For x equal to 1, the value of y is 1. In the same way as x changes, y also changes. Right. This gives rise to the concept of limits. Suppose I tend x to a certain point. Right. We don't know what is x0, or let it be a general point. So I take x very much closer to x0 and I observe where does y moves to. Where does y moves to? Suppose y moves to a point called L. Right. So what's happening here? As x moves toward x0, the variable y moves towards a value L. Right. If we have such a situation, we may say that the function y has the limit L as x tends to x0. So let's make it formal. Suppose we have a function f of x, say f or f of x. We may say that this is the customary notation to denote the limits. Limit x tends to x0, f of x equal to L, if as x tends to x0, f of x tends to L. Right. So we may say that limit x tends to x0, f of x equal to L, if as x moves to x0, f of x goes to L. Right. So let's go to an example. Say f of x equal to x square be the function, right? So what is limit x tends to -1 f of x? Let's go to the graph. F of x equal to x square will be a parabola opening upwards with a vertex at the origin. Right. So this is -1 here. This is 0. This is 1. Perfect. So we let x to move towards -1. X is marked on the x-axis. But on the x-axis you have two choices of movement. You can move either from this side or from this side to -1. Right. You have two choices of motion, from this side or from this side. Right. But if you move from either side, the value of f or the y value moves towards 1. Right. Either you move from the right side or you move from the left side, the value of y or the value of f or the function value moves to a single point 1. So using this expression, you may claim that limit x tends to -1 f of x equal to 1. Similarly, you may note that limit x tends to 1 f of x is again 1, which will be of to 1. We may be moving from this direction or from this direction, but whatever, the function will move to this point, right, which is 1. Right. It's a rough graph. Okay. So the key points here are, there may be more than one way to approach the point, and if we both approach from both of these directions, if our function value converges to a single point, we may say that that single point to be the limit of the function, as x turns to be the x0 value, whatever it is. Okay, So let's see another interesting example here. I don't give you the function, but say this is -1, 0 and whatever. Right. So this is the graph of a function. See, this is whole. This is a whole. Whole means the function is not defined. The function has its definition code here. Right. So this is 1 and this is 3. So if you are asked to find the limit, see, this is the function of a function f. Sorry, this is the graph of a function f. So if you are asked to find the limit as x tends to -1 f of x, as we have done before, this is -1. We have two choices of motion, either from left side or from right side. Right. As we move from left towards -1, the value of the function moves towards 3. Right. Or it's actually constantly 3 here. So as we move or as we approach -1 from the left, the function seems to have a limit 3. But as we move from the right side towards -1, the function has a constant value 1, which means the function is seen to have a limit 1. There is a clash happening. See, as we approach from either directions, we get two different limits. In such a case, we may say that for such a function at such a point, limit does not exist. Right. In such a case where we get two different values when we approach from the left or right, we may say that the limit does not exist. So remember that it is not a necessary condition that the limit should exist for any function at any given point. There are in fact a lot of functions whose limits does not exist anywhere. Right. So now let's visit a few interesting properties of limits. This may also be called as rules of limits. Right. Properties or rules of limit. So the first one is limit x tends to a constant is the constant itself. See, how did we define limits? As x tends to a, the quantity here is supposed to change some word, and the quantity word to it changes is called the limit. But the value here or the subject to be changed here is a constant which does not change whatever happens to the x value. Right. So wherever you shift your x, the k is going to be the same where k is a constant. So the limit of a constant is always the constant for whatever x you choose. Right. The second one is limit x tends to a, x raised to n is a raised to n. So f of x equal to x raised to n is a function, and to find the limit of x raised to n as x tends to a, you just need to replace x with a. This works almost everywhere, not everywhere. Okay, almost everywhere, remember. I mean, this technique to replace x and a, we call that to be the substitution method of evaluating limits. Next one, limit x tends to a, k into f of x. So limit x tends to a constant into a function is a constant into limit x tends to a, f of x. Which means the constant can be taken outside the limit. We will see these in examples. These are quite useful techniques to evaluate the limits. So next is limit x tends to a, f of x plus or minus g of x is equal to limit x tends to a f of x plus or minus limit x tends to a g of x, which means the limit of a sum or the limit of a difference is the sum or the difference of individual limits. I repeat, the limit of a sum is the sum of individual limits, and the limit of a difference is the difference of individual limits. Okay, the next one. Limit x tends to a f of x into g of x is equal to limit x tends to a f of x into limit x tends to a g of x, which means the limit of product of two functions is the product of individual limits of the function. Similar for division as well. Limit x tends to a f of x divided by g of x can be evaluated as limit x tends to a f of x divided by limit x tends to a g of x. Remember this comes in the denominator, so this has to be non-zero. Limit x tends to a g of x has to be non-zero. Remember, this has to be assured everywhere and every time when you have something to be written in the denominator side. Right. So we have one more left. Limit x tends to a f of x raised to n. We have a function raised to the power of n. In such a case, the limit may be evaluated as limit x tends to a f of x all to the power n. Right. So the limit can be taken inside the exponential or the exponent. Right. This is valid if n greater than 0. Remember these assumptions of this non-zero condition and the array or the domain of n. Right. So we will be using these techniques in the examples, or these are actually the most useful techniques which can be used to evaluate the limit of any given function. So let's see an example. Evaluate the limit x tends to 2 9x cube. Limit x tends to 2 9x cube. So this is of the form limit x tends to 2 k into f of x, where f of x is x cube and k, the constant, is 9 here. So that can be taken out of this limit. So it is 9 into limit x tends to 2 x cube. Right. So we have seen that limit x tends to a x raised to n is a raised to n. So we can just replace this x and 2 to evaluate this limit, which will be 9 into 2 cube, which is 9 into 8, which is 72. So limit x tends to 2, 9x cube is 72. According to the definition, this means that as x move towards 2, the function f of x equal to 9x cube will move towards 72. Right. And along with those rules we have discussed a little ago, remember these 2 points, which is very useful. If f of x is a polynomial function, if f of x is a polynomial function, then limit x tends to a, f of x is f of a, the value of the function at that point, if f is a polynomial function. Similarly, if f of x equal to say some g of x by h of x, or f is a rational function where h of x not equal to 0, g of x, h of x are polynomials, and f of x is g of x by h of x, means f of x is a rational function with h of x non-zero, then limit x tends to a, f of x equal to f of a, similar to that of polynomial functions. Right. So this gives us the information that for a polynomial function and a rational function which exist everywhere, by existing everywhere we mean that the denominator is non-zero. So for a rational function and a polynomial function, to evaluate the limit, you just need to find the value of the function at that particular point.